lecture 33. So yesterday we were looking at the difference between binary and thermometer weighted D2A converters, and we saw that while a thermometer DAC has the advantage of requiring lot less precision on the individual elements that go to make up the DAC, the complexity of decoding is very high. Okay. On the other hand, in the binary case, the decoding logic is very simple, but the precision demanded of the unit elements that make up the DAC is very large when compared to the thermometer case. Okay. And we saw that when we meant precision, we derived the precision needed, which was denoted by this ratio sigma I by I. Okay. In order to get monotonic behavior, in other words, for the same DNL, all right, statistically, we saw that a thermometer DAC requires lot less precision on the or the requirements on sigma I by I are a lot less in the case of a thermometer DAC. So one other thing that we also need to look at is to see if there is any difference between the two cases. As far as we saw that DNL, definitely you are doing much poorer when you do a binary weighted design. The question is the INL any better or worse? Okay. So let's take again the 4-bit example. Let me take say some code, say 0101. Okay. What does this correspond to? 5i, right? But in reality it is I0 plus I2, correct? And I0 is a random variable with mean I and a standard deviation sigma I. I2 is a random variable with mean 4i and a standard deviation of 2 sigma. All right. So what is the and these are two uncorrelated random variables. So what happens to the variance and mean? The result is that you have something with a mean 5i and a variance root 5 and a standard deviation of root 5 times sigma I. Okay. So what is the INL? What is the definition of INL? It is this minus 5i divided by I. Okay. So that will be a random variable of variance root 5 sigma I. Okay. So let's see what we would have if we had so this is for the binary case. For the thermometer case, what would we see? If the code was 0101, how many of those unit elements would be on in a thermometer case? 5. Okay. So 5 unit sources will be on. Which means that the output is a random variable with mean is 5i, correct? Root 5 sigma I. Alright. So what do you notice here? So whether you do binary or whether you do thermometer, the INL is the same. It's only the DNL that is vastly different for the two cases. Okay. So if you're only interested in INL, which is not often the case, then it doesn't really make a difference whether you do binary or thermometer, right? But in most cases, you're very insistent that the DAC should be monotonic, in which case the matching requirements on the unit elements becomes extremely tight for a binary design. Okay.
So the bottom line is both binary weighted and thermometer
statistically the same.
As we
surmised towards the end of last class, what did we say? We said that it should be possible to combine. I mean, on one side you have one extreme where the digital area is very large and the analog area is very small. Okay. On the other hand, you have something where the analog area is very large and the digital decoding logic is very simple. So, it's a reasonable thing to assume is that there is most likely to be a sweet spot somewhere in the middle where the analog area is not as much as it would be for a pure binary weighted design, okay, and the digital decoding logic would be not so large as you would need for a full thermometer design. Okay, so such designs are often called segmented So on one extreme you have the binary weighted alright, and on the other extreme you have, and you can so if you kind of talk about the percentage segmentation as as some kind of metric which tells you how segmented the DAC is, then the binary weighted case corresponds to a situation where there is no segmentation at all, right, and the thermometer case corresponds to a situation where the DAC is completely segmented. So you break up, if there are if it's a 10-bit DAC, you break up the whole thing into into 1024 equal unit elements, and you turn on the number of unit elements that you need. Okay, whereas in the binary weighted case they're all bunched together in large chunks. All right, so this is the okay. So let's take an example. So again, let me take a 4-bit converter. So can somebody suggest what I should do?
So one idea is that you have 4 bits, right? So B3, B2, B1, B0.
All right. There are many ways of doing this. One way is, for example, take I don't know. Let me say he suggested 1 bit, but I will treat this as the sum of 2 DACs. Okay, one which is controlled by B3, B2, all right, and one which is controlled by B1, B0. Okay, I will implement this in a thermometer fashion. So, please note that the output should be B0 I, or rather B3 times 8I plus B2 times 4I plus B1 times I, B1 times 2I plus B0 times I. This is the ideal output I want. Okay, so I can treat that as the sum of 2 DACs, correct? This DAC, in principle both these DACs can be implemented with, what is the difference between these 2 DACs? I can treat this
I can treat this as the output of one DAC and this is the output of another DAC and add the two outputs. I mean conceptually there is nothing wrong with that, correct? So what do you think is the difference between the two DACs? It's just that the full scale of the two DACs is different. These are two 2-bit DACs. However, the full scale of the first DAC is 4 times the full scale of the second DAC, correct? Does that make sense? And now each of these DACs I can implement whichever fashion I like. Okay, each can be, if both of them are binary weighted, it is equivalent to one full big binary weighted DAC, correct? If each of them is thermometer, it is equivalent to one full thermometer DAC, correct? But perhaps it is possible to implement them. I can realize this DAC using a full thermometer and this DAC using a full binary or vice versa, correct? So let's see what happens when I implement this as a full thermometer DAC, okay, and this as a binary weighted DAC. So one advantage is immediately obvious. What is it? When you have a full thermometer for the whole 4-bit, what do you think is the decoding complexity? Is proportional to 2 power n, is about 15, right, or 16. This is the, so a full thermometer would have required, the digital complexity would be proportional to 16, right. On the other hand, I only have half a thermometer now, right. So the thermometer is only applied to the MSBs in this particular case, alright. So what do you see? The digital complexity is definitely reduced, correct. So now what can you say about the DNL? Where is it? Okay, if you now do this, what happens if you plot the output of the DAC as a function of the code? What happens? The MSB is being controlled by the two MSBs are controlling a thermometer DAC. So what will the MSB outputs when you change the MSBs by one digital code? What do you think the output will, analog output will jump up by? It will jump up by 4i. So the outputs will be, this is code MSB is 0, right. So this is B3, the code corresponding to B3, B2, and that varies from 0, 1, 2 and 3, alright, and the output jumps up from, please note this is a thermometer, so it goes from 0 to 4, I mean let me just make this is 4i, this is 8i and this is 12i. And what can you say about the, and do you see here that to generate this step, are we subtracting two large numbers? Now how will you realize this MSB DAC? I will have 3 current sources of value 4i each, right? And to get 4i I will turn on one of them, to get 8i I will turn 2 of them on, to get 12i I will turn all the 3 on. So you please note that for every step I am only adding, right? I am not generating an 4i by taking 8i and 4i and subtracting, right, which is what I might do if this was realized as a binary weighted fashion, right. So this is the MSB DAC, correct. And what about the small DAC, the B1 and B0 and B1, okay, I realize it using a binary weighted one, so I have only two current sources, one which is I and one which is 2I. Okay. So within these major steps, I need to divide this into 4 minor steps. Each one of these steps corresponds to B1, B0 varying from 0 to 3, alright, and this goes up to, so this is okay, and then there is, these are all the red dots all correspond to what? The jumps initiated by the major jumps up to here you get by using the thermometer, right? Between that and the, up to here you get by using the thermometer. Between that and the next big thermometer jump, you have binary weighted stuff, correct? So what do you think happens to the DNL? Let's evaluate the DNL. What was the biggest problem in the complete complete binary weighted case? In the full binary weighted case, when the code jumped from say 0 followed by all ones, okay, which corresponds to 7, which is what here now? Which code here? 1, 2, 4, 5, 6, 7. That's, this jump was the biggest. No, was it this jump? Yeah. Okay. So this jump was the one which caused the largest DNL, right? Let's now sit and evaluate if the problem is just as bad now or has improved. Okay. So what is your gut feel? You think things have improved? Why? See, here also we have a binary weighted portion, right? So for example, when B1, B0 goes from 1 to 2, alright, there is you are generating a step of I by turning off the current source of I and turning on the current source of 2I, okay. You are still generating a small value by subtracting two currents, right, which as we know is prone to error, correct. But the problem is greatly mitigated now when compared to a fully binary implementation, simply because in the full binary approach we were generating an I in this particular 4-bit example by, at the mid code we were doing this by subtracting off, turning off 7, turning off 7i and turning on 8i, okay. So clearly this is, since there is a binary weighted portion, that is also happening, but the extent of the damage is a lot smaller, simply because it's only the LSBs that we are turning off. Does this make sense? Okay. So let me see. So let's now sit and calculate what the output DNL between these two codes is. So what are we doing here? Let me call the binary weighted stuff, there are 4 current sources here, let me call them, 3 current sources, right. Let me call them 4i1, 4i2 and 4i3, with the understanding that these are, each of these guys is a random variable with mean 4i and standard deviation 2 sigma I. Alright. Now, and the binary weighted DAC sources, let me call them IA and 2IA, 2IB. So, when the output code was 7, I mean when the DAC input code is 7, so that the output current is nominally supposed to be 7I, what is the output? It is simply 4I1 plus IA plus 2IB. When the code is 8, is 4I1 plus 4I2. So here also you are turning off, I mean see, IA plus 2IB is nominally 3I, correct, and 4I2 is nominally 4I. So you are getting that step also by turning off 3I and turning on 4I, but this is a lot better than doing it, turning off 7I and turning on 8I. Does it make sense? Okay. So the DNL, okay, is basically 4I2 minus IA minus 2IB. This is N 4I comma sigma I. This is N I sigma I, and this is N I root 2 sigma. Oh, I am so sorry, yes, it is 2 sigma. Thank you. Okay. So the DNL or the change, I am sorry, so the DNL is proportional to 4I2 minus IA minus 2IB minus the nominal LSB, which happens to be I. So this is N of I. So this is nothing but the mean is 0 because I have subtracted off the nominal LSB size, and the variance now becomes 4 plus 1 5 plus 2 7. And please note that this is the worst case DNL, correct. There will also be a situation like this within each of these 4 segments. Where do you think that is going to happen? I mean, of course, we all agree that it will now be, if it happens from 7 to 8, the same thing will also happen from 3 to 4, and the same thing will also happen from whatever 11 to 12, okay, and so on. But within, if you discount for that jump, within these red dots, do you think there is a problem also? Yes, when you jump from 0 1 to 1 0, you will also have a similar problem. You are generating, going from 1 to 2 by turning off I and then turning on 2I. But the magnitude of that problem is root, I mean the standard deviation corresponding to that is only root 3 sigma I, okay. So so definite and quite clearly this is the absolute worst case. So what has segmentation done? It has dropped the worst case DNL, which was square root 15 sigma I, to square root 7 sigma. Okay, and you know we shouldn't sneer at this reduction, okay, as being just half, simply because, in other words, all this is saying is that the sigma I by sigma I by I that can now be tolerated for this level of to get this for the same DNL has now is 1 by or rather you can tolerate root 2 times the the mismatch, which corresponds to, if you had to do that, so if you reduce the area by a factor of 2, mismatch goes up by a factor of root 2, because please note that mismatch is proportional to 1 over square root area, right? So, so this basically means that the whole DAC size can be, the size of the current sources can now be half. The size of the decoding logic has also gone up, alright. However, it has gone up by, when compared to a pure binary DAC, how much has the size of the decoding logic gone up by? A factor of 4, correct? Because if you assume that the complexity of a simple binary DAC is just 1, okay, you have to now generate 4 lines from the 2-bit code that you get. The 2 MSBs will be generating 4 lines, correct? And you basically will end up with something which a decoding logic which is definitely more complicated than the binary case, pure binary case, okay. But you can see that you are saving a lot of stuff you are saving a lot of area in implementing the current sources, because they can now be more mismatched, and you will end up with still the same DN. Does this make sense? Okay. So now so this is what is called 2+2 segmentation, isn't it? So I have taken the first 2 MSBs and realized a thermometer. The 2 LSBs are realized using a binary weighted affair. Can somebody comment on, should I be doing the thermometer for the MSBs or for the LSBs? I just discussed, we just discussed this thing where we realized these guys as B3, B2 as a thermometer and B1, B0 as a binary weighted one. An equally valid approach at first seems to be, why should we particularly single out B3 and B2 to be implemented in a thermometer fashion? We could have said B3, B2 would be binary, and B1, B0 will be thermometer. So any comments on that? So if there is, see, whenever you have a binary weighted design, there is this majority code transition problem, right? So you want to make sure that the LSBs of the binary weighted portion are as small as possible, right? So it always makes sense to realize the MSBs as a thermometer and the LSBs as a binary weighted affair. Is that clean? Is that clear? Okay. Now, now that we have ironed that out, another alternative way of segmenting it could be 1+3 segmentation. Any comments on this one? What does this 1+3 segmentation mean? The thermometer has got only is a 1-bit DAC. So the thermometer has got a single current source of value 8i, and the binary weighted one has 3 current sources. What are all those 3 current sources? IA, 2IB and 4IC, where IA, IB and IC are all, what do you call, random variables. So what about the 3+1 segmentation? This is where the thermometer has got this thermometer has got, wait a minute, this is 2i, 4i and so on up to 14i. It's got 7 current sources. Pardon? I'm sorry. Yeah. Blah blah blah. Right, and the binary one is either 0 or, it's got a single current source of value I, and it's either turned on or off. So any comments on this one? This is not quite as the same as a full thermometer, right? So what do you think this is going to be better than the what is it, 2+2 segmentation, or worse than it? Decoder complexity is now is twice as digital decoder complexity is now is 2x the 2+2 implementation, because there you need to take 2 lines and generate 4 lines. Here you take 3 lines and generate 8 lines. Okay. On the other hand, the DNL, what is the worst case DNL now? When it changes from 7 to 8, for example, what do you get? So you have when the code is 7, you have nominally 2i plus 2i plus 2i plus I, right? And when you have code is 8, you have these 2 current sources will remain the same. In fact, all these 3 will remain the same. Okay. So when you subtract it out, it is simply you are subtracting the difference between a current source of value I which was on, you are turning it off, and then instead turning on a current source of value 2i. So what is the DNL is proportional to N0 root 3 sigma. So you can see that clearly. I mean, you can think of this as a 75% segmented design, right, and this as a 50% segmented. As you can see from this example, the larger the amount of segmentation, or the closer the segmentation gets to 100%, I mean the benefits kind of accrue. Okay, I mean it's not as if there's a you're not getting anything for free, right? A reduction in the analog area has to be accompanied by an increase in the digital area. That's what the conclusion is. Yes, sir. So the question is, okay, why don't we do this, which is you have 2 DACs, one which is I, 2i and 4i, another DAC which is, okay, alright, so what now? If one is always on, this is 7i, okay, this 7i, okay, so this is controlled by B3 is what you're saying, is it? So you have 2 DACs, so I, 2i, 4i, what is this controlled by? So B0, B1, B2, so the output of this DAC will be B0 times I plus B1 times 2i plus B2 times 4i, okay, what else? Okay, so this will be B0 I plus B1 into 2i plus B2 into 4i into B3, okay, alright. So how does this work now?
When you go 7 to 8,
Wait a minute, when we want all 15, are we getting 15 first of all? Yeah, so this is, I mean when you go from 7 to 8, correct, it's equivalent to having, this is equivalent to having, what do you call, an 8i times B3, isn't it? That solves the problem when you go from 7 to 8, but when you go to 14 you will not get it, I mean 15 you will not get in. Okay, that's equivalent, I mean so what you're saying is exactly equivalent to having current source of 8i turned on and off. So it turns out that that as the segmentation is increased, you progressively get to a better DNL. So if you know how much area your decoder what do you call adds, okay, I mean how many square microns of area you need to realize a certain number of gates, then you can go and figure out a segmentation which will give you the optimal area, right? So I mean this I think is pretty straightforward, and I think I'll give that as an exercise for your assignments. So you can go and figure out the percentage of segmentation required to get the complete DAC in the smallest possible area, and that clearly has to do with the trade off between the analog and the digital area. Okay. So it unfortunately it turns out that it's not just random error. I mean, this is all comes under random mismatch of current sources. Okay. In practice, the current sources in the simplest case are realized using, you know, a MOS transistor operating in saturation. So one way of and what you need to do is basically, if you have a current source, what do you want to do? You want it to be able to either connect it to the output, okay, or connect it, dump it into some other place where, what do you call this, is say B and this is B bar. Okay, so you want to be able to steer this current either into RL or dump it somewhere. That's the basic idea, right? Yeah. The question being asked is, why bother trying to throw the current away? Maybe you will be saving power if you just leave this floating, right? So you just leave it like this. When B is on, current goes into this node RL, right? Or is getting sucked out of RL. When B is off, you know, it's an open circuit. In theory, that potential will go to minus infinity. In practice, you know that the transistor will get into, what will happen? If I do not connect anything to the load here, what do you think will happen to the transistor? The drain source will be equal to 0. Okay, all right. So the question is, what is the problem with that? Right, you could be doing that. So any guesses on what the problem might be? See, anyway, there's always going to be parasitic at this node, right? So when you turn it on, this node voltage will have to again charge up to, from 0 it will have to go up to some value, okay, and in that process it is not as if when you turn this on, instantly it's becoming a current source. This transistor becomes a current source only when the VDS is greater than VGS minus VT. So until the time duration beyond which the drain source potential goes higher than VGS minus VT, that the transistor actually acts like a resistor, right? So that will cause all sorts of, you know, weird problems, because you are expecting only a current source, and now this guy behaves like a resistor for some part of the time and behaves like a current source for some other part of the time. So it turns out that will cause a lot of distortion, and that's something that you do not want. Okay, so the idea must be to keep the transistor in saturation and make it behave like a real current source throughout. Okay, and that's easily accomplished by making sure that this potential, okay, is such that the transistor is in the active region all the time. I have shown an NMOS current source. This could as well have been a PMOS current source. Okay, so conceptually what you need is something like this. You have a current source. During some part of the cycle or whatever, when you want the current, this goes to some load resistor, and if current is flowing, current always flows from a higher potential to a lower potential. So presumably the topmost terminal of the resistor, that is this guy here, cannot be ground, correct? So let's call it has to be a high potential, so let's call that VDD. And when you do not want the current, you can dump it off, okay, to some other path. You understand? Conceptually, this is what you want to do. So can you think of a simple circuit which will let me do this? The simplest thing that you can think of which will do this is the differential pair. So this is B and this is B bar. Okay. Now, as I told you earlier, you know, you always, I mean, for a whole bunch of reasons, it makes sense to use fully differential signals, right? So you're not only interested in, I mean, the output voltage here will be if this is VDD, this voltage will be VDD minus IR times B, right. So if B is 1 logically, alright, then the output voltage will be VDD minus IR because all this current is flowing in the right leg, alright, and clearly you can see that if there is any noise on VDD, it will directly come out at the output of the DAC, okay. So instead of that, what would you do? You are anyway throwing away this current, so you are planning to throw away this current, so if you treat the output of the DAC not as a single voltage but the difference between these two node voltages, what do you see the output to be? So this is VDD minus IR times B bar, correct. So the differential output voltage is nothing but, if I call this, now I will call this VOP and VOM. VOP minus VOM is nothing but 2 IR times, I'm sorry, it's B minus B bar I guess, right, or is it I? So this is either plus or minus, yeah, it's plus or minus IR, alright. So this is the unit cell of a, I mean the simplest possible unit cell of a 1 bit D to A converter, okay, fully differential. Now if I wanted to make a binary weighted DAC, what would I do? I will take this, copy and paste, so B3 for a 4 bit example, this will be 8i, this will be 4i, blah blah blah, and I simply add up VDD R, okay, and this is VOP, this is VOM. So this is an example of a binary weighted DAC, and since it basically operates by steering current in one direction or the other, right, such DACs are called current steering DACs, and these DACs happen to be the most popular architecture used to realize D2A converters today, and the reason is they are capable of very high speed operation simply because as I was telling you, you always keep this the current source alive, nothing is turning off or turning on, so you don't have to keep, I mean you just, the current is always flowing, you are just steering it one direction or the other, okay. And while I have shown B3 and B2 and all that to be logical signals, they are logical 1 and logical 0, but in reality all that you need to do is make B3 and B3 bar the difference sufficiently large to steer current this way or the other. How much voltage do you need roughly to steer a differential pair? What does that depend on? You know that the voltage difference required between the two input terminals of the differential pair, if you recall from earlier classes, if I plot the difference between the currents in the legs of the differential pair, so I1 and I2, okay, if I plot with respect to the difference between if I plot the differential input on the x-axis and the differential drain currents on the y-axis, when Vn is very very large and positive, what happens? All the current gets steered to one leg, right? Then the difference is 0, it's like this, and then it's an odd characteristic, so it does this, correct? So And what does this width depend on? What does that width depend on? It depends on the VGS minus VT of the transistors, correct? So please note that this slope is proportional to the GM of the transistors, correct? So if the slope is very small, it basically means that the GM is small. For a given current, if the GM is small, what does it mean? The VGS minus VT is, for a given current, the transconductance of a transistor is proportional to 2I by VGS minus VT. So if the slope is small for a given current, it means that the overdrive voltage, the VGS minus VT of the transistors is large. Okay. So at any rate, this transition region, which is what we'd like to operate typically in analog applications, is precisely what you don't want here, right? So you want to be able to switch quickly. So in other words, the VGS minus VT the difference between the two voltages required is only of the order of a few VGS minus VTs. This, in other words, this B3 and B3 bar need not go all the way from 0 to full rate. Okay, so the swing required here is actually quite small, and if voltages have to swing less, presumably they take lesser amount of time to do so. So this is a good current steering DACs are good candidates for really high speed operation. Okay, and not surprisingly, they are actually very popularly used in use. And okay, so there are, see, most of the basic ideas in DACs are actually very simple. And in principle, there is you learned all that there is supposed to all that there is. Okay, the rest of it is only just grinding through the details. Okay, and obviously it's not possible to do that in a it'll be quite boring, and you won't be able to appreciate it also, because you'll say okay, whatever, right? So you'll a lot of these design details you'll be able to appreciate only when you actually sit and do and design a DAC. And then you will find that, oh my god, there's like this small thing and there's that problem and this problem and all that, and you fix everything, and then you have a workable DAC. But in an introductory course like this, all that one can do is basically, look at the broad design considerations and some of the second order effects that I will go into tomorrow. So hopefully this week I should wind up with DACs, and from next week we can start oversampling AD converters.